Assalamu alaikum everyone. Today we have to start this chapter number 6, which is about the understanding of the process conditions. And in this chapter we will mainly see that what is the allowable temperature and the pressure limits for any process, and what is an acceptable range for those temperatures and the pressures, and if we go beyond those temperature and the pressure limitations, that then what kind of equipment we would require, and how it can influence the cost of the material that we are going to use to manufacture any equipment. Okay, so in this chapter we will mainly see that how we can actually control the temperature, and how the pressure it can affect the process condition, and we will see that if we can play with the temperature and the pressure around the reactors, then how we can actually control the production of the products. So let us see what we have in this chapter in more detail. So the ability to make an economic analysis of a chemical process based on PFD is not proof that the process will actually work. Okay, so we have done studied chapter number 1, 2, and 12, and we have seen a lot of PFDs until now. And we have also seen that how we can actually calculate the process economics and the process feasibility by using the compositions of the products and the compositions of the raw material depending on the market values of the products and the raw material. But whenever we make that PFD, we are not assured that the process can actually work. Okay, so we have to see all the constraints that we have in the system, whether if we are, for example, if we are specifying some temperature and the pressure conditions that is not allowable for any kind of material that is being used for the manufacturing of any equipment, then that process is not feasible. So we have to remain within the physical limits of the process and the physical limits of the equipment or the material of construction. Okay, so we have to increase the sustainability of those equipments, and we have to avoid any maintenance costs that could raise by increasing the temperature or the process conditions. That is why we will see that what is an acceptable temperature and the pressure limits for any equipment. Now, analyze reasons for selecting specific conditions. So whenever you are designing any process or the PFD, then you have to specify the temperature and the pressure conditions and along with the composition. So we have to analyze all the reasons from the process point of view and from the material point of view to handle and sustain those kinds of temperature, pressures, and the compositions. Okay. Analyze process conditions that require special consideration, and we can go beyond the acceptable temperature and the pressure conditions for some special cases, but we have to justify the reasons for going beyond those acceptable temperature pressure conditions. So now let us see some of the heuristics that we have to follow. It is easier to adjust the temperature and pressure of a stream than to change the composition. So what we can actually do here, it is easier for us to change the temperature or to adjust the pressure of the stream rather than changing the composition, because the composition we are having some constraints that we cannot change the composition of the feed stream or the product stream, because it has to pass through some process. For example, if the some reactant is going to convert it to be converted into the product, then it depends on the catalyst that we are going to use in that process. So we are limited with the controlling of the composition of the feed stream or the product stream. What we can actually do, we can only play around with the temperature and the pressure conditions while remaining in the physical limits of those equipments. The following conditions do not cause severe difficulties. So these are the temperature and the pressure conditions that do not cause any severe difficulties, and we can actually easily achieve these kinds of temperatures and the pressures for any process. For example, the temperature between 40 to 260 degrees C, it is very usual in the process industry, and we can actually achieve these temperatures very easily by using some kind of heaters or some kind burning of the fuel gases. So these kind of temperature for the process streams can be easily achieved. Then the same is the case with the pressure. We can achieve the temperature pressures up to 10 bar by using some kind of compressor or the pumps depending on the liquid or the gases. So this temperature and the pressure range, it is within the range that is easily operatable and do not cause any severe difficulties for the process. Conditions outside the above favored temperature and pressure ranges are identified as conditions of the special concern. So if we are making any process that is designed over the temperature and the pressure ranges that are specified here, then we have to justify the reasons for going beyond these temperature and the pressure ranges. Now, in terms of pressure, what can actually happen if we can go up and down uh, as compared to the allowable limit of the pressure. Now, if you are going beyond 10 bar or above 10 bar, then what actually happens? We have to design an equipment with a thicker wall, and it will increase the cost of the equipment. So, obviously, if we have to create some equipment or the vessel at above 10 bar, then we have to increase the thickness size of the equipment or the wall of that equipment. Okay, so that will increase the cost of the overall equipment, and ultimately it will also increase the cost of the production of the products. Then we have to see the safety issue. So when we are going above the 10 bar, then we have to see some of the safety issues also. If some emergency happens, and how what would happen with the equipment. There could be an explosion, and there could be a damage to the process and also to the operator. So if we are going above this 10 bar pressure, then we have to see these two things in more detail for when we are designing any process. Now, for the temperature range between 1 to 10 bar, it is favorable condition, and usually this pressure conditions can be easily achieved by using simple compressors and the pumps. Now, if you are going below the 1 bar pressure, then what could actually happen? We have to use the large equipment, and that would ask for the special construction material, and that will increase the cost of the process. Now, why the equipments that are operating at a pressure of 1 bar would be larger? So it is quite general that the material expands 4 to 5 times under vacuum. Okay, so when we are operating some stream or some process under vacuum, then obviously the things will expand. Then we have to increase the size of those equipments, that would ask for more cost of the equipment, and that will ultimately increase the cost of the products. So special construction materials would be required if we are going to design some process below 1 bar pressure. A decision to operate outside the pressure range of 1 to 10 bar must be justified. Okay, so most of the times we have to increase the pressure beyond 10 bars. So now we have to come up with a very good justification to go beyond a 10 bar pressure for designing any of the equipment. So we will see that what are the conditions that can justify if we are going to go beyond this 10 bar pressure. Similarly, in terms of temperature, elevated temperature, what would happen? It will decrease the physical strength of the construction material. So when we increase the temperature of any process, it will affect the physical strength of the materials, and it will drop the physical strength of the construction material, and replacement by more costly materials. And sometimes if we are going to design a process that is beyond the acceptable temperature range, then we have to use some kind of expensive materials to withstand that high temperature without having any damage to those equipments and the vessels. Okay, so we will see that what are those conditions in which we can go beyond the acceptable temperature range. Now here we have one example here, and we will see that how the temperature can affect the strength of the material. The maximum allowable tensile strength for a typical carbon steel and stainless steel at ambient temperature 400 degrees centigrade and 550 degrees centigrade is provided below. So you can see here the temperature for the carbon steel, the grade is 70. At ambient condition or 25 degrees centigrade, we can have the value for the physical strength 1190. And if we increase the temperature to 400 degrees centigrade, we can see that there will be a decrease in the physical strength value of the carbon steel to 970. And if we simply increase the temperature to 550 degrees centigrade, we can see that there is a sharp decrease in the physical strength of the carbon steel. So we can see that by increasing the temperature, the physical strength of the material, the carbon steel, it is decreasing. The similar cases with the stainless steel. So at ambient conditions, we can have the physical strength of stainless steel type 302 to be 1290. And when we increase the temperature from 25 to 400 degrees C, there will be no change in the physical strength of this stainless steel. But if we change the temperature from 400 to 550 degrees centigrade, then we see that there is a certain decrease in the physical strength of this material, stainless steel. So you can see here that there is half of the physical strength of this material would be reduced by simply increasing the temperature of 150 degrees centigrade. So this is how the temperature highly affects the physical strength of the materials, and we have to consider the temperature as one of the very important parameter when we are designing any process, keeping in view the material of construction for the equipment that we are going to use in the process. Now let us see one more examples in terms of numerical. Determine the fractional decrease in the maximum allowable tensile strength relative to the strength at ambient conditions for the temperature interval ambient to 400 degrees centigrade and 400 degrees centigrade to 550 degrees centigrade. So we will see that what is change in the physical strength of the material when we are increasing the temperature from 25 degrees centigrade to 400 degrees centigrade and then 400 degrees centigrade to 550 degrees centigrade. Now here the temperature interval ambient to 400 degrees centigrade, we can see that carbon steel, what is the value at the ambient condition, 1190, and then what is the value at 400, so 970. So 1190 minus 470 divided by the original value at ambient condition, so we will see that 0.818. So we can see from here that there will be an 18% drop in physical strength of the carbon steel if we increase the temperature from 25 degrees centigrade to 400 degrees centigrade. The same is the case with this stainless steel. If you calculate the decrease in the physical strength of this material, now what we can see here in case of stainless steel, that by moving from 25 degrees centigrade to 400 degrees centigrade, there will be no change in the physical strength of this material. So we can see in this equation that when we put the value, so there will be no drop in the physical strength of the stainless steel. However, if we change the temperature from 400 to 550 degrees centigrade, then the physical strength of both of the materials will be decreased. So we can see here carbon steel, the strength at 400 degrees centigrade, it is 970, and when we're moving to 550 degrees centigrade, then we can have 170. So we can put the values here and we can see that there will be a decrease in 67% of the strength when we are moving the temperature from 400 to 550 degrees centigrade. In case of stainless steel, we can see that the temperature at the strength at 400 degrees centigrade is 1290, and at 550 it is 430. So we can see that there is 67% drop in the physical strength of the stainless steel by increasing the temperature from 400 to 550 degrees centigrade. Now we have seen that this temperature range 400 to 550 degrees centigrade, it is very critical to some of the materials that we commonly use in the industries. Mainly if you look at the equipments material of construction, then most of the equipments they contain the steel. And here you can see this graph here, and you can see that how the physical strength of the material decreases by increasing the temperature. Now here on the left hand side we are having the pressure, and on the right hand side we can have the temperature, and these bars they shows you the material strength. Now you can have this line here which is basically the grade A low alloyed steel. So you can see that if the temperature is increased from 0 to almost 350 degrees centigrade, the material strength it will remain same, but after that it will suddenly decreases. Okay, so we can operate the process within the allowable range of this material. The same is the case with the other materials that we have in this process. For example, if you're using the carbon steel, then the similar profile we can see here. There will be a constant physical strength up to maybe 350 degrees centigrade, and then it will be suddenly decreased. And then for some other grade of the carbon steel, you can have this curve. So for different materials, you can see this kind of curves here, and this will give you the information about physical strength and how the temperature can actually affect the physical strength of the materials. Now, a decision to operate above 400 degrees centigrade must be justified. Okay, so if you are going to design a process which is going to operate above 400 degrees centigrade, then you have to provide the justifications for the selection of this temperature, because this temperature can affect the material strength of most of the materials composed of carbon or the steel alloys. Okay, so we have to see the reasons if we are especially going above 400 degrees centigrade temperature. Now, here we can see that if the temperature range is between 42 to 60 degrees C, so this is comes under the domain of okay. So this temperature, it can be easily controlled by using simple heaters or by simple heat exchangers. We can achieve this temperature. Now, if we are operating some process which is going below 40 degrees centigrade, then we need to have some kind of refrigeration. Now, in case of this refrigeration, we are again provided some of the guidelines that some of the cooling can be done by using some air coolers, or we can use the cooling towers containing water. And if we further want to go beyond that limit for the refrigeration, maybe minus degree centigrade, then you have to use some kind of special refrigeration cycles to reduce that temperature. Now, on the other hand side, if we are going to above 260 degrees centigrade, then you have to use some kind of special heaters that can achieve this high temperature, and they should be, their material strength should be allowed to maintain this kind of temperature. Now, if the temperature of any process stream or any process is below 40 degrees centigrade, then we have to use some kind of refrigeration process. Okay. Now, use as much cooling water as possible. Now, our first thing for any cooling requirement of any process stream is that we can use the cooling water from the cooling towers. So it can further reduce the temperature to 25 or maybe 20 degrees centigrade. So we can actually use that cooling water to reduce the temperature of the process stream. And after that, if the further requirement for the cooling is required, then we can use the refrigeration water or the refrigeration unit here. Okay, and then we can have some kind of separation process. Now, operating cost table 8.3. Okay, so if you go to your book and see this table 8.3, there you will be you will see different kinds of materials and different kinds of utilities along with the cost of those utilities. For example, if you want to use the cooling water to cool some process streams up to 30 degrees centigrade, then you can have the cost of those that cooling water to be 0.354 dollars per gigajoule. Similarly, if you want to refrigerate any process stream, then you have to spend $13.11 per gigajoule. Now here you can see that this amount is going to reflect the amount of energy that you are recovering from the process, or amount of energy that you are supposed to spend on any refrigeration. Okay, so this much is the amount of energy along with the cost that you want to that you have to spend on any process. Now, do we ever operate outside these limits? Now, either we can operate outside these limits or not. Obviously, no process is impossible, but if you want to go operate outside the acceptable limits, then we have to choose some special materials with having some special material of construction to allow that process to operate in those temperature and the pressure conditions. Now, table 6.3 and 6.3, it reflects you the reactor and the separator part. So we will discuss the reactor and the separator part in this chapter in more detail in the coming lectures. For the other equipments, there is a detail. Now for the other equipments, we have to see the table 6.4, and that will give you some more information on the temperature and the pressure conditions for the specific equipments. And now a DME process, a dimethyl ether production process, pretty much inside the limit. So you can see this example of the DME process, and you can see that most of the process streams, they are within the allowable pressure and the temperature ranges. Now let us see what could be the conditions in which in which we can go beyond the acceptable temperature and the pressure ranges. Now the conditions outside the favored temperature and the pressure ranges include: the first one is the favorable equilibrium conversion. A favorable equilibrium conversion, it is basically showing you giving you some information on the Le Chatelier principle that we have studied earlier. Okay, now what is that Le Chatelier principle? That to push the equilibrium on the left or the right hand side, we can manipulate with the temperature and the pressure conditions, and depending on the number of molecules in the equation, and we have to see the stoichiometric reactions, and then we can actually have an idea that the Le Chatelier principle would suggest in forwarding the reaction, or it would be having a negative impact on the process. So it is indirectly reflecting the Le Chatelier principle. The second thing, increase in the reaction rates. Now we have to see what is the reaction rate and how it can be influenced by the temperature and the pressure conditions, and we have to see what is the rate of reaction, and if the rate of reaction can be increased by increasing the temperature or the pressure, then we have to provide the reasons on this thing, and then we can go for the selection of the special material or the material of construction of that reactor or the process streams. Third one, maintain a gas phase reaction. So there could be some limitation on the phase of the reactions or the phase of the process streams that we are going to use. So if you want to maintain some gas or the liquid phase in any process, then we have to provide the reason for using some special material of construction to meet that requirement. Sometimes we can increase the temperature and pressure to improve the selectivity of the product. So in that particular case, we can go beyond the temperature and the pressure condition. So all of these four parameters, or all of these four things, it will directly affects the product purity, so, or the product quality. So if we want to increase the product quality by increasing the temperature and the pressure conditions, then we can justify the process needs. Okay, otherwise we have to remain within the process limits. Now we can have these kinds of table 6.1, it will go until say table 6 point maybe 7, and we can have different things within these tables, and we will see, we'll compare the reactors and the separators part, and we will try to see the reasons if we can go beyond the operating temperature and the pressure conditions. So we will see these tables in more detail in the next lecture. Thank you.